In this video, we talk about a kinematics problem in which two objects are moving and interacting. So we start with two cars moving the same speed, but the car that's in the lead suddenly slams on its brakes, inducing a leftward acceleration and slowing down, and eventually the car behind that slams into the car that's been braking. So one thing we're ignoring in this problem is the width of each car. I'm not concerned about that. So we're kind of pretending that the cars are just point masses. And what does it mean for the two cars to collide? It means that they're in the same place at the same time. So to get a handle on the problem, what we do is write down an equation of motion for car A. That's position as a function of time. And then write down an equation of motion for car B, position as a function of time. And then we're going to solve that system of equations to find the special time where the two positions are the same for these cars. In other words, they've just had a collision. So I'm going to start by getting those equations of motion up here. And I'm using the first kinematics equation for this. And I put a subscript of capital A on all the quantities there. And I'm going to take my origin to be the original position of car A. So X is going to be 0 there. And I'm doing that because I want to find the location of the crash relative to car A's initial position. So we may as well put the origin there. So the initial position of car A is 0. And the acceleration of car A is 0. It just keeps moving at 40 meters per second. So I get this very simple equation of motion. The velocity is 40. So the position is given for all moments in time by just taking 40t. Next, I look at the equation of motion for car B. And this equation is more complicated. The initial position of car B is right here, 50 meters to the right of the origin. The initial speed is 40, so I have 40t there. And then I have an acceleration that has to count as negative when I put the direction in it. So negative 12 meters per second squared. And again, you should notice that when the acceleration is in the opposite direction of the velocity vector, that's an object slowing down. So I'm going to go ahead and simplify as I go here. If I put in negative 12 for the acceleration of car B, and then I have a 1/2 out in front, I end up with negative 6 t squared. So let's get into question A. How long does it take for the cars to crash? So what I do is I say let the two positions be equal. And then we're going to find out what time it is, and we'll have that unique time where the positions are the same and the cars have hit each other. I can cancel these 40t's, and I'm going to add 6t squared to both sides. This is a quadratic equation, but because the linear terms canceled, I don't have to use the quadratic formula. I'm just going to solve by isolating t squared. T squared is 50 over 6, which is 25 over 3. And t is going to be plus or minus the square root of 25 thirds. Now we don't care about the negative answer because the physics of this problem didn't begin until t equals 0 when that driver applied their brakes. So we just keep the positive root, and keeping 3 sig figs, I get 2.89 seconds before the collision. In part B, I want to know where does the crash occur relative to car A's initial position. So that means we're just going back and finding the position of car A, and if we want to check our work, the position of car B as well, when t is equal to 2.89 seconds. So I go to my equation of motion for car A, that's 40t. And what time is it when they crash? 2.89 seconds. And keeping 3 sig figs, I get 116 meters right of the origin. As a check on my work, I can also evaluate the position of car B, and it better be at the same place. The equation of motion was 50 plus 40t minus 6 times t squared. And keeping 3 sig figs on this, I end up with 115 meters, a discrepancy that we can blame on compounding rounding errors throughout the problem. In part C, we're asked for the relative velocity of the cars when they collide. So relative velocity, if two objects are going in the same direction, would just be the difference in the speeds. Like if a 40 meter per second car ran up on a 20 meter per second car, there's a 20 meter per second difference between them. So it's the relative velocity when they crash. If two objects are coming at each other, the speeds would add. And to answer this, we're going to get the speed of each car. And so for car A, that's simple. It's still going 40 meters per second. So I'll call that VA. Is 40 meters per second. But car B has been accelerating. So I have to use my second kinematics equation for this. V equals V naught plus AT. and the initial speed was 40 and the acceleration was negative 12, and it was doing that for 2.89 seconds before they crashed. So when the collision occurs, keeping 3 sig figs, the speed of car B was 5.32 meters per second, and it was still moving to the right. So my relative velocity, because the cars are going in the same direction, is going to be the difference between these two. And keeping 3 sig figs, I end up with 34.7 meters per second, meaning that car A was moving 34.7 meters per second faster than car B when they hit. If you find the physics content on Zach's Lab helpful, click on the Zach's Lab logo on the right to browse playlists and subscribe to the channel. I produce over 100 new videos per month, and subscribing is the easiest way to find new content. Thanks for watching.